Good morning. Thank you very much for joining us today. So I'll just kick us off with a little bit of admin and housekeeping. Welcome to the webinar. I will shortly hand you over to Casey and Jack. This session is being recorded, so if you have any technical issues or you need to jump off, the recording will be circulated afterwards. We'll take some questions as we're going along. There should be a Q&A box for you to submit any questions you have. We'll either answer those as we go along if we can, or at the end there will be some time to have a bit of a discussion. And I'll be managing those at the end of the slide. So without further ado, I will hand you over to Casey.
Fantastic. Can you hear me okay? Sweet. Okay. Morning, everybody. I hope you've got the hot beverage of your choice and you're sitting comfortably. I'm going to talk about heat networks and rising energy costs, the relationship between them, and some of the things that can be done to mitigate the effects of rising costs. A little bit of background first. We go on to the next one, Charlotte. Am I in charge or are you in charge, Charlotte, of slides? You are. Okay, cool. So a bit of background about Guru Systems. We provide Internet of Things technology to make energy systems more transparent, lower cost, and lower carbon. That involves putting electronic devices, communications networks, and server-side software in place on heat networks, cooling networks, other on-site energy systems, and also increasingly in standalone heating systems in dwellings to better understand how they're working, ensure that they're being metered properly, support things like payments, and crucially, for the context of this conversation, supporting the process of improving those energy systems and their performance. The company's been going for over 9 years. It'll be our 10th birthday this summer, which is pretty exciting. We're in the low 40s in terms of team size, but it's growing quite quickly. We've delivered our system to over 40,000 homes across the UK, and that's from Glasgow and Edinburgh all the way down through England and into the southwest. Our systems have carried over 1 million payment transactions. In addition to metering, we also do pay-as-you-go utility platform and control. Did you mean to skip ahead there, Charlotte? There we go. And that the data that comes out of our system is frequently used to help support the process of improving those energy systems, as I mentioned. And it's not rare for those improvements to be on the order of 70% heat loss reduction from heat networks. Our clients tend to fall into three main groups. We've got housing associations and local authorities as one group. We've got private developers and build to rent as another, and we have the large energy companies. But all three of those groups of clients, they have the same sets of issues on distributed energy systems and heat networks in particular. So I think whichever of those that you might fit into personally, I think that what we're talking about today is relevant. So should we go on to the next one? So we've had a price rise already, a rise in the price cap on gas and electricity. We've got another one coming up later this year in October, or expected to come up later. And the cumulative effect is over a doubling in the price cap over the course of this single year, and that's absolutely massive. It's estimated that something like 6.5 million households will be pushed into fuel poverty as a result. This is a huge impact on a huge number of households across the UK. While I think that the price cap discussion has got a fair bit of airtime, one of the things that isn't appreciated is the fact that customers on heat networks are not protected by those price caps. So our starting point for the discussion today is actually, while energy prices are rising, they're rising for heat network customers in a different way than they are from to domestic customers of gas, for example. So that's some of the background to this. So there's the wider context of the energy price cap rising, but for heat network customers, they're not protected. And as we're going to discover, the performance of the heat network then amplifies the costs of the gas that's coming into the plant room. Should we go on to the next one? There we go. How are they impacted? Well, heat networks are typically supplied by a single heat supplier. So you've got a plant room, probably on a typical network, you'll have a plant room or an energy center that is operated by the heat supplier in most cases. They've got a bulk supply of gas coming into that plant room. They're then generating that heat somehow, doesn't matter what the plant is. It may be a bulk electrical connection going into a large scale heat pump. In any case, they're producing heat in that energy center. The heat is then being distributed to all the customers on that site via a closed network of pipework. So in other words, the water is just carrying thermal energy from the plant room to the end customer. Customer takes the thermal energy, the water goes back to pick up more thermal energy and repeat that loop again and again. Homes on heat networks are supplied by a single heat supplier. They are natural monopolies. You cannot, in most cases, you cannot switch away from the heat provider on a network. The heat supplier themselves, who controls the incoming gas contract, they can change gas supplier. Without a price cap, suppliers can pass on wholesale costs in the commercial supply of energy. So as those costs on commercial supply are going up, driven by the rise in wholesale costs, that can get passed through to residents without a cap. The generation of heat in the plant room is only the first step on the journey, right? So you've either got gas or bulk electricity being converted into heat, and that gets you to the boundary of the plant room. But what happens next is crucial, because the performance of the network, the heat network that goes from the energy center to the residents, then is an amplifier of the incoming energy price. And we're going to look at that in more detail. If we were all in the room together, which we're not, at this point, I would pause and say, is that clear? Has anybody got any questions so far? If you have got any questions, please put them into the chat. And Charlotte, if there's something contextual that we need to pause and talk about while we're going, just stop me. Okay, super. So let's talk a bit more about inefficiency as a multiplier of the underlying gas cost. And although we said gas here, I just want to be really clear. If it's a electricity supply into a large scale heat pump, the principle is exactly the same. So the way to think about this is that the useful heat demand in a dwelling is what it is. The amount of heat that a dwelling requires to satisfy space heating and domestic hot water requirements are let's imagine that they're a fixed number. So the key question is, how much energy, how much heat do you have to put in at the energy center in order to get that amount of useful heat out? The extra energy that you have to put in at the energy center is all about the losses on that network. So it's how much heat is that heat network losing in transit between the energy center and the resident. That's the extra energy that has to be put in. So just at an intuitive level, it's really easy to imagine that if you have higher losses, then to get the same amount of useful energy out at the dwelling level, you've got to put more energy, more heat energy in at the plant room, and therefore you've got to burn more gas or consume more electricity, right? That's the intuitive picture. Now, if we dig into the detail behind that, so imagine that on a good network, and this is the box on the left, on a good network, let's imagine that 20% of the heat supplied to the network is lost. And therefore, it's 80% of the energy, of the heat energy leaving the plant room that's then useful at supplying that demand within the dwelling. The cost per unit of heat at the point of generation, so this is after the boiler or the heat pump, gets divided by 0.8 because 80% of it is useful, which means, or multiplied by 1.25, same deal, exactly the same, to arrive at the cost per unit of heat consumed by customers. So when we're talking about a multiplier of the underlying heat cost, then in the case of a network that has where 20% of the energy being put in is being lost, the multiplier is 1.25. And let's imagine that's on a sufficiently good network. Now, what about on a poorly performing network? Well, let's imagine that 70% of the heat supplied on a heat network is lost. And so only 30% of the heat energy leaving the plant room is useful. Therefore, you've got to put a heck of a lot more in to supply that fixed amount of demand from the dwelling. In that case, the cost per unit of heat at the point of generation, so just downstream of the boiler or the heat pump, gets multiplied by 3 1/3, 3.33, to arrive at the cost per unit of heat consumed by customers. It's on the next slide in just a sec, but just to point out, on a decent network, we've got a multiplier of 1.25 of the heat cost at the plant room. And on a poorly performing network, we've got over 3, a multiplier of over 3. So an absolutely massive difference, the way that the underlying cost gets amplified. And you can quickly see that on a heat network then, the rise in the gas price is only the first part of the story, or the rise in electricity, only the first part of the story, because all of that then gets amplified up by the performance of the heat network. Okay, so those are the principles. Let's look at it now in a slightly more visual way. Okay. So this is the same idea. I'm actually going to start on the, let's go on the left-hand side, right? So losses as a percentage of input energy, and then the equivalent heat cost multiplier. So we already covered the case where it was 20% losses, and we saw that it was a multiplier of 1.25. And we've seen the 70% case where 70% of our energy is being lost as heat losses on the network. And that's a multiplier of 3.33. We filled some values in between here. So 30% losses is 1.43, 40%, 1.67, 50% is now 2, which if you think about it for a minute, makes a lot of sense. 60% is 2.5. Change that into a pound figure. And by making some assumptions about standing charge and input price of fuel, and I appreciate that those details may change depending on your particular heat network, but the shape of this line, the magnitude of this line is what's most important on the right-hand side on this graph. So what you can see is that as the heat losses increase, they increase reasonably shallowly in terms of cost, and then it really starts to ramp up beyond about 40% heat losses. And you can very quickly go 3x or 4x what you would find on a good performing network. Okay, so the effects are potentially thousands of pounds in cost to residents, which starts to put into context just how important it is that not only do we need to keep the input fuel cost reasonable, we also need to ensure that the heat network is working well to keep that multiplier as low as possible so that prices are low to residents. Okay. Anybody please throw questions in the chat. Charlotte, is there anything I need to pause on?
You've obviously explained it perfectly because there are no questions.
Yeah, either that or there's nobody here. I mean, it could be either one, right?
I'm confident it's the first.
Okay, cool. Great. Let's go on to the next slide. So we did a piece of work for Bayes, going back some distance. This is back in sort of 2016, 2017 time. And we looked at, I think, coming for about 40 networks. And what we found was that heat networks were not working, mostly were not working as well as had been expected. And in many cases, they were only delivering about 36% of input energy as useful heat out. So, do the maths, that's 64% losses. That was an average of the sites. And there were outliers in both directions. What we tended to find was, one, everybody had much better intentions at design, install, and even into operation, more like design efficiencies of 80% or more. And two, that the networks that performed well were the ones that were monitored. They were the ones that were watched. Somebody was getting some data, checking how the thing was working. If it wasn't working, they were then taking action to put it right. So the important takeaway here is that networks have the potential to have very high losses. And if you go back several years, it didn't matter if they were new or old. This wasn't a function of age of the networks. It was just, were they watched and operated well, or were they not? Go on to the next one. So what do we want to do here? Well, we want to get the data from heat networks and use them to identify whether or not they're working. The old adage about you can't manage what you don't measure is fundamentally true here. And what we've seen again and again is where it's not measured, you can bet it's not performing well. So I can't think of any time in the last 10 years when we've got involved in a site where nobody had been watching, and when the data started to flow, everything was fine. That has never been the case. Data has the potential to show what's going on at the dwelling level, what's going on at bulk metering level, and at the energy center. And it's important to, I suppose it's important to say, where's that data coming from? It's coming from, on a heat network, it's coming from heat meters. There is a requirement to install heat meters on new networks, right? So you've got them at the dwelling level. There's a legal requirement to install them at block level. So those are going in. And you've almost certainly got energy center meters as well. The usual assumption is that those meters are going to be used to meter and bill people, to take a kilowatt hour read to generate a bill. But what's important to emphasize is that meter has got lots of really valuable performance information in it: flow and return temperatures, flow rates, cumulative volume, cumulative energy, instantaneous load. There's all this precious information in there that the meter knows from moment to moment, not just once a month when you want to generate a bill. So, and those are assets that have to go in anyway. This isn't a question of putting in additional metering to get this done. This is a question of getting the best out of the meters that you have to put in. You take that data and you can direct the interventions to improve efficiency. You can work out where the problems are, and then you can ensure that they're put right. And that then helps to reduce the cost. In the short term, there's an urgent need to do this now. And also longer term, it helps you stay on the front foot operationally to ensure that if problems arise in future, that you're catching them early and taking early action. I'm going to hand over to Jack for this next part.
Thanks, Casey. Yeah, my turn. So, hello everyone. So, Casey's kindly taken through all the sort of general thoughts and ideas and so on around network efficiencies, but I'm going to start going into a little bit more detail on what you can do with the information that we can get out of these buildings. So, I'm going to talk about sort of what a good heat network looks like, what a bad heat network looks like, and then on the poorly performing networks, what kind of problems you can use. You can use the performance data to spot and what to do with that information to help keep the resident bills low. And then we'll finish off with a couple of real life case studies to show how poorly performing networks have been turned around using performance data as that, as the starting point. So this graph probably looks a little bit chaotic, but if I quickly run you through it, it's pretty simple once you've been shown. So this has been pulled out of Guru Pinpoint. And actually, what we're looking at here is meter data, so energy meter data that's come from an individual dwelling. The horizontal axis is time. The left-hand vertical axis is flow. So we've got meters, meters cubed, and then on the right-hand side we've got the vertical axis is temperature. The bottom light blue line is the flow rate, and the green line is the return temperature, and the dark blue line is the flow temperature. So that explains what this graph is. All the data that's that used to compile this graph is high frequency, so 5-minute data that comes out of a standard meter. So basically on any HIU you can that's got a meter attached to it, we connect to that meter and we pull that data out. So this is available. This is just standard information. That's what Casey was just saying in the last his last example. So what we're looking at here is the day in the life of one dwelling on a heat network. It's in East London, and although it kind of looks all over the place and chaotic, this is actually what a really well performing dwelling looks like. So when heat is demanded, you can see that the flow rate increases. The light blue line at the bottom has little peaks, and then generally what happens is you can see that you've got an instant reaction with the delta T. So suddenly the blue and the green lines widen, and they kind of match one another. You can see all the way along they're matching. And what this means is that you've got really good thermal transfer. It means that when the demand is there, it means that the thermal energy has been taken out and then used in the dwelling. So this is this is exactly what you want to see at dwelling level. If all dwellings are performing like this, then you've generally got a really well performing network. If anyone's got any questions about this chart, because I know it's it might take a few minutes just to get your head around it. We're about to have a look at another couple now. So if you do have any questions, pop them in the Q&A, and we'll get those answered on the next slide. So Charlotte, can you move along? Yeah, great. So when you look in comparison to the previous charts we've been looking at, we've got two poorly performing dwellings here. So if you look at all the colours and axis and so on are the same on these charts. If you look at the top dwelling here, we've got really, really tiny delta T. So the flow and temperature is essentially exactly the same. If you squint, it's kind of like a bit of a magic eye. They sort of merge into one. They're so tight. They're so tightly linked. And then the flow rates are actually really high. So if you look at the box on the flow rate there, we've got 0.029 meters cubed per hour that's running through that HIU. So that's 29 litres an hour that's running through the HIU, and none of that thermal energy is actually being transferred to the dwelling. So all that was just basically doing absolutely nothing. All it's really doing is probably turning hot water back to the energy centre, which might cause overheating in the corridors as it makes its way back. And then if there's a boiler on the network, it's also likely going to affect whether it's condensing or not, which is another inefficiency issue. The second graph we've got here is a dwelling where something suddenly goes wrong. So you can see before the arrow, but 4/5 of that chart, things are behaving relatively well. We've got a nice wide delta T. It's you can see that the flow and return temperatures are reacting to the changes in flow rate and so on. However, about midday on June 20th, something happens and it all changes. So you can see so an area like this can happen occasionally when a resident starts tampering or a tenant starts tampering with their HIU. But more than likely, this is an unscheduled maintenance visit, sort of, probably in response to a customer reporting that they've they're not getting hot water quick enough to their taps. And what happens is an engineer will turn to site, quick fix, turn everything up to maximum, and while it's actually fixed the tenant's immediate issue where they can get, you know, boiling hot water to their taps a bit quicker than they were before, possibly, it's actually going to mess up the whole system. And the reason I say mess up the whole system, it's because it only takes one poorly performing HRU to throw off the network. So when performing well, an HRU may see, say, 4 litres an hour pass through it. So quite a low amount, you know, quite a low flow rate. However, when the settings are wrong, this could be as high as 400 litres per hour. So if you've got if you have a development where you have 100 HRUs on that are all designed to have a 4 litre per hour flow rate, and one of them is returning high temperature water at the same rate as all of the other HRUs combined, this is why it's really important to monitor the performance of each dwelling. So poorly performing heat networks don't always perform poorly for the same reason. So some aren't designed well, and these are probably the more problematic ones to fix, you know, possibly oversizing and so on. So interventions are possible, but they can be complicated. Some are designed really well, but they haven't been commissioned properly, acceptance testing hasn't been carried out, and so on. They haven't been checked before the residents moved in, and then it's, you know, and then generally things don't get fixed until, you know, until the nth hour or ever. But then some are checked, but then they'll drift over time, and this isn't, you know, it probably isn't due to equipment failing. It's more than likely something like, you know, what's just happened above, where small changes over time to the system by people that possibly aren't referring back to the design, or maybe aren't aware actually that what they're doing is wrong, can have a cumulative effect and then actually put the system out. So even, you know, even the best systems handed over in exemplar condition still need to be monitored for performance over time. Okay, so enough of the graphs. You'd be pleased to know. So in our time working in heat networks, we've seen all of these problems, you know, and as Casey said, you know, as soon as you start looking at the data, then you start finding these issues. And actually the majority of these issues on here literally can't be spotted unless you start looking at the data. The key is to work with a partner or in-house who understands heat network performance to help you fix the problems in both the short and the long term. So this may not be existing O&M partners and contractors. You might actually have to go to someone more familiar with heat networks, you know, real experts. You know, even some of the best heating engineers do not understand heat networks. And we find you'll be finding now, if you're having new developments, a lot of the consultancies now have got dedicated heat network teams. You know, it's a department within the consultancy. It's not just, you know, it's not just the same people that are insisting, you know, that were speccing these things a few years ago. You know, it's been taken a hell of a lot more seriously, and off the back of that, there are a lot more sort of dedicated consultancies that are actually working in the industry now. So once you start get this data out of your buildings, then you can start spotting inefficiencies. You can make interventions which will lead to lower energy consumption for your heat supplier, or for the heat supplier, and then these savings can be passed on to help, you know, lower the residents' bills. It's then important to monitor ongoing performance to ensure the systems stay on track too. So this isn't a one-time intervention. It's, you know, it's continuous, and there is still improvements. You know, you can get to a really high, you know, really exemplar level, but then still find inefficiencies, you know, if you keep monitoring it. And as we've seen in the previous example, ongoing monitoring is really important, even where the networks are well designed and properly commissioned before residents move in. So I think the key takeaway from this slide is, if you don't have the capacity to stay on top of the heat network performance in-house, just go and find someone and work with them who, you know, that know the trade and can do this, and who can help. Okay, next slide, please. So now we're going to have, so we've been looking at a bit of detail in the previous slides. We're going to have a look at a couple of case studies now. So these are looking at overall schemes. One of these, if you know us, you may recognise the first one, as it's a project that we've talked about before, and the second is a site that recently won a Subsidy award for good performance. So in this case study, as both landlord and energy supplier, Network Homes had previously charged residents a flat rate for their energy it supplied, and it was unable to monitor energy consumption in individual properties across the network. I think some of you on the call probably recognise this. You know, if you've had developments handed over sort of pre-2015, there's a chance that you didn't have meters on it. Pre-2014, 13, you know, you probably don't have meters in a lot of these developments. So it's very common. In this case, using performance data, Network Homes were able to diagnose that the heat interface units hadn't been commissioned properly and were poorly performing, which was resulting in really high return temperatures. And the data collected also inspired site investigations, which found missing insulation on the pipework. So a small intervention there. The results were actually huge. So 53% reduction in heat network losses were achieved by monitoring, you know, by starting to monitor this development. And it just goes back to what Casey was saying earlier. You know, you never go into a project that doesn't have decent monitoring on it that are running really well. You know, it was pure data that exposed all of these issues. They knew they had a problem, but it was the data that exposed where and how to fix it. 40% reduction in terminal run temperatures versus ambient for dwellings with interventions. 60% reduction in terminal run losses for dwellings with interventions, which saved more than 1,700 kilowatt hours per annum across the site. A £140 saving per household per year after resident heat consumption reduced by between 20 and 30%. And obviously it's worth noting that since this project, the cost of heat has more than doubled. So you'd be looking at these interventions would be saving nearly £300 per day. So today. Okay, next one, please, Charlotte. This is a more recent project. This is the one that won the Subsidy Building Performance Award. It's a project we ran in collaboration with Fairheat, so Echo Court. And the project involved data-led acceptance testing, so the new process defined by CP1 2020. If nobody's heard about this on the call, we've got a load of literature that we can help you with, and we can talk you through what this is. It's great. I won't go into detail here, but it's going to change. It's going to change things for the better. Guru Hub 2s are installed across this particular development, and performance data was used to ensure that the network was run into design before the residents move in, and that's key. You know, getting this done before the residents move in means that it can be fixed, because this is usually the problem. Commissioning is put back to 1 or 2 days before practical completion, and then you just can't get back into to fix things. Fairheat estimated during the review process that they would be able to save each resident around £160 a year, and then reduce the scheme's carbon emissions by 72 tonnes per year. And you think these calculations were actually carried out in 2019, so the savings to the residents is going to be, you know, it's going to be far more, you know, over £300 given today's energy prices. And interestingly, Fairheat also used existing knowledge of the performance of HRUs to make the right selection for this development too. So performance data from existing heat networks can be used to help the heat network design of the future. This is something, again, that's really, really important, you know, particularly now that you start working with your consultant engineers on new developments. Give them the data, go back to them and let them learn, because this is a real problem for them. And I know they're all super hungry for this information, where as soon as they hand over a project, that it's either, you know, they either dust their hands and say, okay, that was a great success, but not really know anything more than that, or they're getting badgered because there are problems with the system, with the system. You can actually go back to them with this data. It will help inform what they do on future projects. You know, you might find that a particular HRU works for a particular setup and a particular dwelling type, you know, or you might find that that the boilers or the heat pumps were oversized on a particular dwelling because the rule of thumb was, you know, was out by a factor of, you know. So just, yeah, once you start capturing this information, go back and use it again to inform future projects. Next one, please. So we're just about out of time, but before we move on to the Q&A, I just want to pull out these final points. Again, it's something Casey mentioned earlier, the old adage, you can't manage what you don't measure. Well, there's also sort of a little bit more to it than that, where don't do the bare minimum either. You know, your meter and billing requirements are 30-minute, you know, 30-minute data coming out of each dwelling, which can tell you a little bit. Just make sure that the systems that you're specifying can get you more high frequency data, and they can get you all of the metrics that come out of the meter too. So there's more, you know, super important. There's no point scrimping and saving 10, 15, 20 pounds to value engineering that out, when actually you could potentially be saving that weekly, you know, by having this performance monitoring that sits on top of the infrastructure that you're putting in anyway. So this performance data that you get out of site can help reduce costs for residents in both the short and the long term. In the short term, this might be sort of smaller interventions like HIU recommissioning, or smaller capital projects like extra insulation. And then in the longer term, there might be more targeted solutions for bigger problems, which will also help to lower costs relating to maintenance and frequent call-outs and so on. But overall, better performing heat networks can save money for residents over time. So if you don't have the skills in-house to stay on top of heat network performance data, you just find a partner who can help you do it. And that's it, I think. Yes. So super. Thank you so much for listening. If you have any questions, write them in the chat, and Casey and I will attempt to answer them now. Otherwise, please drop us an email. Our email's on here. Or if you want to speak to either of us individually, we're obviously happy to do that too. So I'm going to just pass you over to Charlotte, who's been making notes of all the questions that have come in so far. Thank you very much.
Thank you very much, Jack. We've got a little bit of time. We have a couple of questions. We'll see how many we can get through. So one of the first ones was, why is there no price cap on gas supplied to heat networks?
I'll take that one. Okay, so the price cap is domestic supply price cap. So it applies to domestic supply of gas and electricity. When we go back and we look at the model that I was describing before about a heat network has residents, so effectively domestic supplies at the end of the heat network, but coming into that energy center are bulk gas supplies that are almost always considered commercial gas supplies. And the energy price cap does not apply to those. And as a result, you get the exposure of heat network customers to these increases in commercial gas and electricity cost that would be ultimately capped in a purely domestic setting.
Excellent. I guess that kind of leads nicely on to how can the government help customers on heat networks with price rises if this is the current situation?
It's a straight up follow up, isn't it?
Yeah, okay, so I'll take this one too. Okay, there's a lot of focus from people like Heat Trust and the ADE on this right now, and there have been meetings, for example, with the business secretary and the energy minister to talk about exactly this point. So to flag up that customers on heat networks are exposed in this way that is out of sync with the exposure of other residential customers on the system. The things that government can do, the things that government need to do are, first of all, the question is what level of financial support would be required in order to bring parity between residential heat customers and residential heat network customers and everybody else. It's not clear what that mechanism might look like. There might be a number of ways of cutting that. It doesn't look like the government is going to take particular action on that front. I think where that's got to is Treasury is going to take it away and look at it, which, may be an indication that an answer won't be forthcoming. Another thing is HNS. So I'm not sure if you're familiar with the heat network efficiency scheme. It was piloted, or it's currently being piloted now. It's about a £4 million program of retrofitting, or rather improving, remediating, let's say, existing heat networks to bring their performance up. There's a whole crop of projects that have come through that pilot. We're working on about half a dozen, I think, and the results have been excellent. So when you go back to these existing networks and you ensure that you've got the systems to get the data out, you make use of that data to underpin remediation, then the results are in line with those case studies that Jack was showing earlier, and in some cases, outliers a lot even better. One of the things that government might do is there's a follow-up to HNS, which is going to be the post-pilot full kickoff of the program. It's always been scheduled to start in the spring of next year. I think it's about £30 million that's been earmarked. Not a lot. I mean, it sounds like a lot. It really isn't a lot of money given the work that needs to be done and the urgency around it. There's been a push to bring that work, to bring HNS forward. I'm not sure that's going to happen. I think probably we're going to have to wait until the spring. But there is work that you can do to prep for HNS coming into being in the spring. So if that's something that's on your radar and you want to discuss, let me know. Ultimately, price regulations coming in. So we know that Ofgem, as of June last year, Ofgem is officially named as the regulator for this space. We had the Queen's Speech, we've got the Energy White Paper, we've got primary legislation coming up, but there's then it's going to take secondary legislation. It's going to take time for Ofgem to ramp up, and we're probably, 3 years away maybe from Ofgem taking the chair. Now, when they do, their remit will cover pricing on heat networks. So if it's 3 years from now, we've got a ready-made regulatory lever that we can pull in order to address this problem. But that's 3 years away, and there is no price control on heat networks until that point.
Perfect. Thank you, Casey. That's great. That's all we've got time for. Thank you both for going through that with us today. Much appreciated. And the recording will be circulated. And as Jack mentioned, please get in touch if you have any follow-up questions or you would like some of the supporting literature around these issues.
Thanks very much.
Thank you very much.